We're now going to take a look at confidence intervals. And first of all, really what a confidence interval is say we're looking at a distribution and we think about what value is in the middle of that distribution. It is our population parameter. So if we're talking about confidence intervals here for a mean, we're really talking about in the center of that distribution is our population mean score. What if we don't know what the population mean is? Well, this is what a confidence interval is all about. We don't know what the population parameter is, so what we're going to need to do is to make an estimate for what that population parameter could be. Well, if we're talking about the population mean, what value could we possibly use as an estimate for that population parameter? What we could go and do is to take a sample, and then within that sample, find the mean value of the sample, and use that as our estimate. So again, we have no idea what the actual population mean is, but we run a sample, we get the mean from that sample, and we use that as an estimate for our population parameter. But what we should know at this point is that there is no way we are going to get that bang on. There's no way that the value from the sample that we take is going to be the exact same value from the population. So we shouldn't just say that our sample value is an exact estimate for our population value. Instead, we're going to have to take into account that we are going to make mistakes, that there is something that we can never avoid, sampling error, and we know that our sample statistic will never be a perfect reflection of the population parameter. So instead of saying our sample statistic is an exact estimate for the population parameter, what we'll actually say is that our population parameter should fit within a certain range of values. There'll be a low end of the estimate and a high end of the estimate. Well, how are we going to find those? It will be all based around our sample statistic, in this case x bar. We'll factor in some error. So to get the low end of the estimate, we're going to take the value that we calculated, x bar minus some error. To get the high end of our estimate, we'll calculate x bar plus some error. And then we'll say within a certain confidence level, so maybe we're 90% confident, maybe we're 95% confident, 99% confident, that our population mean falls to within some low value and some high value. And that's really what we're trying to do here. So let's look a little more in depth at some specific terminology that we're going to see. First of all, the point estimate. Well, every single population parameter has a point estimate that is the equivalent sample statistic. So as we just saw, if we're talking about the mean, the sample mean would provide a point estimate for the population mean. We know that's not going to be an exact match. So the confidence interval reflects the fact that we will be making some mistakes, and we're not going to say that the population mean is exactly equal to whatever value we get for the sample mean, but within a certain range of values and with a certain amount of confidence, we can figure out approximately where that population value should fall. So again, we should always remember that we will never perfectly reflect the population parameter with the sample statistic. Sampling error is something that can never be eliminated, and the confidence interval gives us an idea really of how sure we can be about how accurate our point estimate is. To make the confidence interval itself, one thing we're going to need to know is the level of confidence plus what we've already talked about, the level of significance, will always be equal to 100%. So remember previously when we talked about level of significance, we said level of significance is the same thing as a type 1 error. This is that error in the tails of our distribution. The probability of rejecting our null hypothesis when it is actually true. When we're talking about a confidence interval question for mean, we will always need to use a t-score. if we think about why we would need to use a t-score and what differentiates a t-score from a z-score, remember for both of them we need to be able to assume a normal distribution. And now where does the actual difference come from? For a z-score, we need to have the population standard deviation. For a t-score, we will have to calculate the standard deviation from the sample. And if we think about what we're trying to do here, we're trying to estimate what the population mean is. If we don't know the population mean, well then there's absolutely no way we have the population standard deviation. So we'll have to use a t-score since we will never know what that population standard deviation is. The formula for the confidence interval first really comes from what our t-score formula is. So we know that t is equal to x bar minus mu over s over the square root of n. What we're trying to do here is solve for mu. We're trying to figure out what mu is, so we want to rearrange this formula to isolate for mu. So first thing, we'll multiply the denominator of the fraction over to the other side. And then we'll have to isolate for mu. And when all is said and done, rearranging the formula, we should get that mu is equal to x bar minus your t-score times s over the square root of n. We just need to make one little adjustment to this formula. So looking at the formula we have to this point, and thinking about what is actually wrong with the formula, well, if we have our distribution here and we're trying to figure out what our population parameter is, in this case the population mean, using x bar as our point estimate, our formula at this point says that our population mean is equal to our sample mean minus t times s over the square root of n. The problem with the formula is the fact that if I'm looking at constructing, in this case, a 95% confidence interval, that formula only takes into account the low end of what's going on. All that little bit after the minus sign is really the error that we're talking about. And in this case, we would only be able to construct a low end of the estimate. Well, that's not all we want to do. We know that half of that error is on the low side and half of that error is on the high side, and we're going to get a low end and a high end of the estimate. Is to not only subtract off error to get the low end of the estimate, but also to add some error to get the high end of the estimate. So what we should do to that formula to alter it and get it to its final state is to say that the population mean is equal to the sample mean plus or minus a bit of error. Minus the error to get the low end, plus the error to get the high end, and now we have our finalized version of our confidence interval for a mean question. If we're constructing a 95% confidence interval, and half the errors on the low side and half the errors on the high side, really what we're talking about is doing a two-tailed test with the amount of error being equivalent to the level of significance. Remember, the level of confidence plus the level of significance always equals 100%. So if we're doing this question, we're doing a t-test, and specifically a two-tailed t-test because we have some error low, some error high. And we're doing a two-tailed t-test with a level of significance of 5%. 2.5 on the low side, 2.5 on the high side. So again, we have our final equation for a mean confidence interval. Population mean equal to the sample mean plus or minus a bit of error. And that error will, as we said, come from a t-score because we will only have the sample standard deviation. It will come from a two-tailed t-score because some of the error is low, some of the error is high. And the probability associated with that two-tailed t-score comes from our level of significance, the amount of error that's in the low tail and the high tail combined. If you're asked to construct a 90% confidence interval using a two-tailed t-score, you would use a level of significance of 10%. Because we know that the level of significance and the level of confidence will always equal to 100%. So the level of significance can always be found by taking 100% of your distribution, subtracting the confidence level that you want to obtain, And with that information, you should be able to find the t-score for that part of the formula. The rest of it will all come from calculation. Calculating what your sample mean is, calculating what your sample standard deviation is, and calculating what your sample size is. So now let's go and do a question and put the theory that we just talked about into use. Looking at this question, we have that a retail chain would like an estimate for the mean spent by all customers. In order to do so, the retail chain surveyed 400 random purchases. The sample showed that the customers had a mean purchase amount of $500 with a standard deviation of $100. First off, we're asked, can we assume a normal distribution, and why? Remember, there are different questions we ask ourselves, whether the question is about mean or the question is about proportion. So here it is definitely a question about mean. It's told us an average amount purchased. It's given us a standard deviation. So for a question about mean, we either have to know whether the population follows a normal distribution, which in this case, we don't have any information about the shape of the population. So without that, what we need to have is a sample size greater than or equal to 30. Well, here we have a sample of 400, so we can assume a normal distribution. Our sample size is greater than the 30 that we need. For part B, what is a point estimate of the population mean? Remember, a point estimate for any population parameter is the equivalent sample statistic. So if we're talking about population mean, mu, its point estimate is the sample statistic x bar. Population means point estimate, sample mean. Well, what is the value for the sample mean that we have in this case? $500. And again, we're not going to go and say that because we went and sampled 400 people, they had an average purchase amount of $500. So therefore, the population mean is also 500. We remember that that point estimate is really only the value that we base our estimate for the population mean around. We know there's going to be error involved. So to find the low end of that estimate, we're going to take 500 minus some error. To find the high end of that estimate, we're going to take 500 plus some error. But in order to know how much error we need to talk about, we have to know how confident we want to be in our decision. The more you increase your level of confidence, the wider your range will end up being for your confidence interval. The less confident you want to be, the narrower your range is going to be. So if we look at part C, it's asking us to establish a 99% confidence interval for the population mean. Well, dealing with a question about mean, our confidence interval formula, now trying to obtain all the bits and pieces of that formula. We already know that the sample mean, our point estimate, is 500. The t-score we'll deal with in a second. The sample standard deviation was given to us for this question. It was $100. And our sample size was also given to us. To obtain the t-score itself, that will only be done with the use of Excel. So let's break away for a second from the slides and go into an Excel spreadsheet to find our t-score. We're going to need to refresh ourselves with something that we haven't talked about in quite a while. We remember that when we're using functions in Excel and we use a function that involves dist, that function will find a probability. Well, that's really not what we're looking for here. Let's look at a distribution to think about what we're actually trying to find. So what we know so far is that we have a point estimate for the population mean, and that will be our sample mean. That point estimate will fall right in the middle of our distribution. What we really want is an interval estimate with a low-end estimate of the interval and a high-end estimate of the interval that will incorporate the fact that we know that sampling error is going to be made. So we're not trying to find a probability here. What we're trying to find is an actual observation. What is a possible value, and specifically what is a possible low value and a possible high value for the population mean? We actually already have the probability that we need in order to find that low-end observation and that high-end observation.
Looking at this information that was given to us, it specifically comes from here, the fact that we're dealing with a 99% confidence interval. Dealing with a 99% confidence interval, we know that the middle of that interval overlaps our point estimate. So if we're talking about a 99% confidence interval, 49.5% of that confidence interval is below the sample mean, or the point estimate, and 49.5% of that interval is above the sample mean, or the point estimate. Because we have to use a t-score, and reminding ourselves again of how a t-score works, a t-score doesn't look at the probabilities contained within the center of a distribution, and it doesn't work like a z-score where it looks at the probabilities below a specific value, or for that matter the probabilities above a specific value. A t-score works always looking at the probabilities in the tails. You need to specify the low tail, the high tail, or both tails. So if we're talking about our 99% confidence interval cutoff, well, the probability we need to talk about with the t-score is exactly what is contained in those two tails. And again, as we've said before, because we're looking at both tails, we're looking at a two-tailed t-test, and the probability that we'll be dealing with, or what percent of the data is contained within those tails, is exactly equal to our level of significance. Or the level of significance in this case, because we're dealing with a 99% confidence interval, is 1%. So again, we're not going to use a dist function because we're not solving for a probability. We're doing the exact opposite. We have the probability that we're dealing with, 1%, and we want to use that probability to find an observation. So we did this previously with the normal distribution. Going one way looking for the probability, we use norm dist. Going the opposite way, using the probability to find the observation, we use the function norm inverse. Well, it is the exact same thing here. So not using t-dist, but using t-inverse. And as we see, a confidence interval will always be a two-tailed test. We want a low end of the estimate and a high end of the estimate. So we will use t.inv.2t. In looking at what that function requires, we need not only a probability, which we've already talked about being 1%, but we also need the degrees of freedom. And the degrees of freedom is always the same calculation. It is our sample size minus 1. Or if we have a sample size of 400, our degrees of freedom are 399. Hitting OK, we should get that we have a t-score of 2.5882072 and probably further decimals beyond there.
With the use of Excel, we were able to find that that t-score is equal to 2.588 and all the other decimals that come with it. Well, now we have all those bits and pieces of the formula that we require to calculate our estimate for the population mean. We get that 500 plus or minus 12.941, and again a series of decimals. Now remember that 12.941, everything after that plus or minus is the amount of error that we're allowing ourselves based on the 99% confidence interval. So 500 minus some error to get the low end of the estimate, 500 plus some error to get the high end of the estimate, and what we should get is that we are 99% confident that the population mean falls somewhere between 487.06, that's 500 minus the error, and 512.94, that's 500 plus the error. So even though we don't know exactly what the population mean is, we are 99% confident that it falls somewhere between that low end of 487.06 and the high end of 512.94. So if we were asked, is it reasonable to conclude that the population mean is $550? Well, if you think about the confidence interval we just calculated, we said 99% confident that was somewhere between 487 and 512. So is it reasonable to conclude that it could possibly be 550? Absolutely not. 550 lies outside of our confidence interval. So it is definitely not reasonable that the population mean would be $550. Looking at one more question. So going through our thought process. First of all, what type of question is it? Is it hypothesis testing? Is it a confidence interval question? Is it a sample size question? We look at what the question's asked us to do. It's asked us to construct a 95% confidence interval. So it is a confidence interval question. Next, is it a question about mean or proportion? Well, again, construct a 95% confidence interval of the mean property value in London. So confidence interval question, dealing with a mean, reminding ourselves what our formula is. We have that the population mean is equal to the sample mean plus and minus some error. So what we're going to need to do is to find all the pieces of that formula. We're going to need to find x bar, t, s, and n. Well, remember, first things first, whether we want to use a t-score or a z-score, first we have to be able to assume a normal distribution. Without knowing anything about the population, we're going to need to have a sample greater than or equal to 30. So the first thing I'm going to do is to count how large my sample is. And it's definitely more than 30 values in the sample. Calculating n, we get that our actual sample size is 312. So now, being able to assume a normal distribution, we can go and finish off the rest of the question. So x bar, the average of our sample, we should get that the average of our sample is 223.793, and I'm sure there are more decimals after that. And remember that using the increase or decrease decimals does not actually do any rounding within the cell. It's just how many decimals are going to be displayed in the cell. So please, this is why it's very important to always use cell references. If we simply went and did a calculation based on the value that we originally saw in that cell, which was 223,793, we would get an answer that was inaccurate. As we can see, there are many more decimals beyond that. The t-score itself. Remember, there are two pieces of information that we need for that t-score. One, what probability are we dealing with? And two, what are your degrees of freedom? Well, the probability we're dealing with comes from our alpha value. So if I'm constructing a 95% confidence interval, well, then we have alpha, or a level of significance of 5%, or 0.05. Knowing both my alpha value and my sample size, I can go and use the appropriate t-inverse function, which we've already said is t.inv.2t. Again, pulling up that function and making sure we use cell references, we have a probability of 5%. We have 311 degrees of freedom. Clicking OK, we see that we get a t-score of 1.9676. And again, I'm sure there are more decimals beyond that, which there are. S, this is the standard deviation from our sample. So we will need to go and calculate our sample standard deviation, making sure that we use the appropriate standard deviation function. So stdev.s, because we are basing our standard deviation calculation on a sample. So again, highlighting all of our data. And with that, we really have all the information that is required in order to calculate our confidence interval for the mean. One thing that I do like to do before I go and make the calculation is to do a separate calculation for the error. The error is really everything contained after that plus and minus sign. So, for our error, what we should have is that the error is equal to our cell with the t-score times the standard deviation over the square root of the sample size, or the sample size to the exponent 1/2, So we get that the error is approximately $4,440. And the reason why I like to do that error separately is now in order to construct the confidence interval, we simply have to take our sample average minus the error to get the low end, and to get the high end, the sample average plus the error. And with that, our question is finished. We get that we are 95% confident that the population mean lies somewhere between $219,353.01 and $228,233.53. I'll show you quickly one other way that you can actually calculate that error within Excel. Now this only works for a confidence interval question dealing with the mean, so please do not use this theory with a proportion question. In order to calculate the error, not the full confidence interval itself, but what the error should be, we can use the formula confidence.t. Using that formula confidence.t, we see that it's looking for several inputs. It's first looking for the alpha value. It's looking for the standard deviation. And it's looking for the size, which is the size of the sample if we read our little information panel. And if I click that, what we should find is that confidence.t formula has not found what the confidence interval is itself, but it has found what everything after that plus minus is, or simply what the error is. So whichever way you want to do it is fine, as long as you realize that now that you have that error, you take your point estimate, your sample value, subtract the error for the low end, take your point estimate, your sample value, plus the error for the high end of the estimate.